So, once again let us review what we had done in the last class, looking at turbulent flows, which is in equilibrium, and what are the time scales those are involved in turbulent flows. We wanted to estimate by looking at this equation that we called as the turbulence energy budget, which actually looks at the energy associated with the fluctuating component of the velocity. And what you notice is the assembly of this term that originated from this governing equation for fluctuating quantity. And as you can see that these two taken together, when it is multiplied by taken a dot product with V, gave us this term. That is what I have identified there. For example, this term comes from the viscous diffusion term here, right? That is what we get. And this term that comes from here, and there is this term that comes from a combination of this and that. This does not give rise to any contribution when you integrate over the whole volume, that we know. So, then we decided to take a look at a special flow, which we called as a steady homogeneous pure shear flow. Steadiness comes from, if I put the left hand side time derivative equal to 0. Homogeneous will say that all quantities, average quantities, are independent of position. They are same everywhere except the mean flow. Okay? That convects the flow, right? That gives rise to the time rate also. So, that is that, and pure shear flow will tell you that del u I del x j, this are pure constant. And if you do that, then you can see what remains is that this is the term that comes from the mean shear, and this comes from the fluctuating quantity. They ought to be balanced, right. So, that is what we looked at, and we further made some order of magnitude estimate, and we looked at that when we wrote that equilibrium condition. On the left hand side, we saw what was happening was basically the turbulence production term, and because it is in equilibrium, so it must equal to the rate of dissipation. So, that is what we are getting. Now, if we circumvent or try to go beyond this specific case of equilibrium flow and look at general shear flow, then also what we would find that these two quantities are of same order of magnitude. They need not necessarily be exactly identical, and this observation is really the basis for developing all turbulence models. We also note that if we define u cap as a velocity scale, L as some kind of a length scale, then the mean shear would be given like this, and the Reynolds stress that we have is also of the square of the velocity scale itself, and we can plug this information in our equilibrium condition to get this following equation, right. So, what we do get is this, that S I j times S I j, time averaged over a sufficiently long interval, is equal to the product of the mean shear times the Reynolds number. And we have already noted that Reynolds number very large for turbulent flows. So, that would show that on a time average sense, the fluctuating strain rate is significantly higher than the mean strain rate. Okay. We have seen the dimension of S I j is of the order of 1 over t. So, the time scale of dissipation and the time scale associated with the convecting process, they are widely separated. This is the reason that one can perhaps do a Reynolds decomposition. This for the same reason that we can talk about unsteady RAMs, because even though the mean may vary slowly, but the frequency of variation is so low compared to the frequency of the fluctuating component that we can say that they are kind of separated so that there is no direct interaction between time average strain rate of fluctuation and the mean flow, provided the Reynolds number is significantly large. So, in a sense you can just simply say it in one sentence that these two events, the mean and fluctuations, they are not tuned to the same frequency band, they belong to a different frequency scales. Okay. Now, if I look at a general shear flow, then we are seeing that the small scale turbulence is independent of the large scale. So, when I am looking at, let us say, turbulent flow over, let us say, aircraft wing, the very fact that I put in a aircraft wing, the eddies are created which are of the size of the dimension of the aircraft wing, right, the chord. So, you could basically look at that, and then what you can see that this small scale eddies do not change under rotation or reflection of the coordinate system. So, basically the small scale is independent of the large scale, and what happens is that the small scales are therefore considered kind of isotropic, because what is happening is you are getting the small scale by successive fracture of the large scale. You have large scale, they break down into smaller scale and so on and so forth. So, when you go to the lowest scale, they have become kind of almost homogeneous isotropic. Okay. This is what is called as a local isotropy assumption of the small scale, and this is used observation is used in large eddy simulation, where you try to derive a model for this small scale, which are anyway not resolved because of your grid. So, you will have to model it. So, you make use of the fact that those scales are isotropic. Okay. So, basically then this is one byproduct of what we have studied looking at equilibrium turbulence. Now, let us get back to this question of relating the mean stress, mean strain rate with the Reynolds stress. What we find that we are again considering an equilibrium condition, and we are talking about a steady state having been reached, and once we have reached that steady state, we get this following equation. So, this is the observation that we would like to make note of, that the Reynolds stress is related to the mean strain when you integrate over the whole domain is determined by the viscous diffusion term. And the negative sign here implies that the overall effect of V I V j integrated over the whole domain has to be of a similar effect like what you expect out of dissipation. So, basically that is why most of the turbulence model are modeled simply as a sort of a overall dissipative phenomena, right. That is what the sign implies, that it is dissipation. Okay. It also shows that they are not completely uncorrelated, right. What has happened, what we just now talked about, the fluctuating strain rate is uncorrelated to the mean strain rate, but here we are talking about a different thing. We are talking about the correlation between the mean strain rate and the Reynolds stress. So, this is the velocity second moment, right, the fluctuating velocity second moment. So, this is also what is done in most of the algebraic or differential equation based turbulence model, where you eventually try to write out some kind of a algebraic relation or a differential equation which relates the evolution operator of this with the help of the mean strain rate. This is what you do in turbulence models. Now, take a simple example for demonstration purpose. Flow inside this passage where the bottom wall is fixed. So, you do not have any slip here. The top wall is simply slipping by at a constant speed, say u or u bar, while the other two components y and z components are 0. So, basically it is a turbulent Couette flow that we are looking at. Now, some of the parameters that defines this flow, of course, is very easy for you to see from the Navier-Stokes equation. The Reynolds number is given by the velocity scale, that is the speed at which the top wall is slipping by. H is the gap between these two walls, and that promotes you to have a exact solution for the laminar flow, because it is a parallel flow. So, you get u is equal to simply u bar z by h. Now, if I want to solve for the turbulent flow, we need to apply, of course, these two boundary conditions. Those two boundary conditions are considered to be time independent, even though the flow is turbulent. And as a consequence, what happens is all the mean quantities are going to be functions of z alone, because we talk about a parallel flow, right. We have a perfect symmetry in the z direction, and of course, there is no variance in x and y direction. Then if I write down this equation, I will get this term. Okay. You can verify that. You can verify that. This term is of course not there. This term is gone, and this term will not be there. Okay, because of your invariance with respect to x and y direction. Okay. So, what you end up getting from the Rance equation is this shear gradient of the Reynolds stress should be balanced by equal to the streamwise diffusion term. So, it is fairly simple, right. This equation is simple. All you need to do is integrate this equation once. So, on the left hand side I will get V 1 times V 2 is equal to nu times du dz, d 1 dz, or 1 is associated with the x direction at height z minus nu of the same quantity evaluated at the wall. So, we integrated it from 0 to running height z. Okay. So, what happens is we have seen that our equation 24 was what? If you recall, equation 24 was Sij. We had written this, right. This volume integral is equal to minus nu times this, right. So, that is the equation that we have. Of course, there is a factor of 2 missing here. So, what will be the simplest possible turbulence model? That should be given by this, because that is what our previous equation has shown. We just simply looked at it in this form, that 28 tells you that V 1 V 2 is going to be proportional to d 1 dz. So, if we try to do that, we can write it down in this particular fashion. Then this will be equal to proportional to this. So, proportionality constant is what we would like to call it as the eddy viscosity. And we have talked about enough to justify why we call it a viscosity, because we saw that V I V j negatively correlates and is proportional to the loss term. So, this also should mimic a loss term. So, that can come about if we position it as a sort of a viscous term. Okay. Now, what is the dimension of eddy viscosity is area per unit time, right. So, that is L square T to the minus 1. What about the dimension of this? Dimension of this is 1 upon T, right. This du dz. So, it is 1 upon T. So, then what happens is this must have this kind of a dependence, because if I want to have this dimension as L square T to the power minus 1, then that L square part comes from here, Z square, and T to the power minus 1 comes from this, and they are proportional. So, this proportionality constant I am calling it as a kappa square, and purposely wrote it as square term. So, that the nu T will be positive, whereas the Reynolds stress will be strictly negative. Okay. So, that is the motivation for writing down this expression for nu T, the kinematic the eddy viscosity. So, we have now seen that u prime provides the time scale, the z, the distance from the bottom static wall to any particular height, provides us the length scale. Kappa is a dimensionless quantity, and it has been shown time and again in various other studies that it is a constant due to von Karman taking a value of about 0.4. One can show that. So, basically then what happens is we have a solution for the Reynolds stress. Reynolds stress is simply given by this. Okay. So, what I do is then I substitute this in that governing equation. After integration we have gotten. So, basically V 1 V 2 Z is this quantity that is written here, and this is equal to this. So, this is the equation that would basically tell you how the shear is varying with Z, isn't it? That is what it is, d u 1 d z at different height. So, it is a kind of a quadratic equation. So, you can solve it. If you solve it, you will be able to obtain it, the expression for u 1 z. However, we can also define a velocity scale in a somewhat different way, where we talk about a wall shear that is dimensionally equal to rho times nu times du dz, right. So, that is the definition of this. So, since we are talking about a mean, so that is why this angular bracket has come, and on the left hand side we have written everything in terms of mean quantity. Okay. So, what happens is if I now divide bring rho on this side. So, tau w by rho gives you a velocity square length scale. So, this is what is called as a frictional velocity. U star is the frictional velocity, which is given in terms of square root of tau wall by rho. So, substitute that expression and you get this equation, that is the quadratic. Okay. So, we have just introduced the friction velocity, and we have obtained a quadratic for u 1 prime z, and that is your solution, straightforward. And so, this is an expression for d u 1 d z, right. So, we can integrate it once again to obtain the velocity as a solution. So, whereas how is it that this is different from a laminar flow? Where has the thing come about? Well, it has come about because of the presence of the V 1 V 2, right. V1, V2, those Reynolds stress would be negligible for laminar flow. So, where does this thing come in? In this equation. In this equation, that information comes in through the way we have defined the velocity scale u star, because the tau wall has a built in effect of the turbulence in it. The wall shear itself has information of turbulence being built in there. So, once we can get this velocity scale, then we can get the solution for the velocity profile, right. How do you get this velocity scale? It is very easy. You have that equation, the solution, and apply the boundary condition. The boundary condition is that if I go at the midpoint, it is linearly growing. So, I get this, right. So, I substitute it there and I get this equation. So, what happens is if I choose a Reynolds number, I can solve this equation for u star, right, because everything else is known. Kappa is a constant and Re is known, u bar is known. Only thing that remains unknown here is this u star. So, I can use this equation for u star, the velocity scale. Once I have it, I can go back and obtain the velocity profile. So, that is a very simple application of the ideas of relating the mean strain rate with the Reynolds stress. That is what it is. So, if I now plot the u versus u1 versus z, then this is the way this velocity profile is going to be. So, it is perfectly symmetric about the midpoint. On this side you have one sign of shear, on this side you have the other sign. So, the plate is dragged along like this. So, that is what you are getting. Okay. Okay. So, you get the maximum velocity u bar at z equal to h. So, this is your mean flow solution, what we called as u1 as a function of z, and having obtained that, we can also calculate the Reynolds stress V1, V2 as a function of z, which will be equal to 0 at the wall, is not it, because at the wall you are going to apply no slip condition. So, no fluctuation. So, its time average also has to be 0. Where will it be maximum? It will be maximum somewhere in the center of the passage. Okay. So, that is what we are going to see, that at the center of the gap we are going to get the maximum Reynolds stress. Well, this is just kind of an exercise. You can spend some time looking at it, that what happens to this value of the frictional velocity in the limit Re going to infinity. That is truly a very high Reynolds number solution. You should be able to show that the frictional velocity has this kind of a log dependence on Re. This is at kappa. Okay, this is at kappa. What you could do is you have a laminar flow solution, you have also a turbulent flow solution. So, from those velocity profile you can calculate tau w, and then you try to plot this quantity versus Re, and then you see what you are going to get. So, do take a look at this, and you will be able to see very clearly the distinction between laminar and turbulent flows. Okay, let us now move on to a different approach. See, so far what we have done, we have looked at turbulence as a kind of a time varying quantity, and we looked at it in terms of its time averaged equation, the Rance equation. Now, we have also of course talked about a little bit about large eddy simulation, but not to a great extent. And talking about time averaged quantities, we have made some of the observations, like the role of Reynolds stress is going to be dissipative in a time average sense. But is it true that it happens at all length scales? We are talking about a time averaged value. So, what we would rather like to know is how the turbulence quantities vary as a function of wave number. And this was what was studied in great detail by Kolmogorov by looking at a periodic flow in a box of size L. Okay? So, I have a cube of size L, and I am also going to look at a velocity vector, which I am writing as u as a function of x and t. I can take its Fourier transform. I can take its Fourier transform to get the spectrum. So, u hat as a function of wave number k, and of course, k is a vector. So, you could have all three components. Now, I could get the spectrum, or if I have the spectrum, I could perform a inverse transform to get the velocity field in the physical plane, right. This what we are doing with the idea of we are looking at a box of size L, and what happens? We are also making an assumption of the flow being perfectly periodic. So, what happens is you are going to get succession of wave numbers in these three directions, which are super harmonic of the fundamental, okay? And the fundamental is given by 2 pi by L. Okay? So, I have it in the I direction, I have it in the j direction, I have it in the k direction, x, y, z directions, and subsequent harmonics will take different values of n1, n2 and n3. So, it is a periodic flow. So, n1 could go from minus infinity to plus infinity. So, can be said about n2 and n3 also. That is what we are looking at. So, once we have defined the velocity field either in the physical plane or in the transform plane, we can invoke what is called as Percival's equality or identity, which is a very simple observation that if I look at the kinetic energy per unit volume, that is what I am going to see it in the physical plane, that is half rho times modulus of u as a function of x and t squared. That is exactly the same thing if I would have written down the velocity in the spectral plane. So, that is what we are doing. So, what happens is whether I look at it in the physical plane or the spectral plane, the kinetic energy represented would be the same. Now, if I consider non-periodic flow with arbitrary conditions, then this summation here would be replaced by an integral. I will have to replace Fourier series by Fourier transform. That is what we do. And what happens to the box size? Of course, the box size is becoming infinite to that extent that we will take L going to infinity, replace this summation by appropriate integral. Now, what you do is this the appropriate integral would imply that I will have to be talking about an elementary volume in k space, that I am writing it as d cube k. What were the individual fundamental frequencies? Those were 2 pi by L. So, I have in each direction I have 2 pi by L as the interval. So, d cube k is nothing but 2 pi by L. So, then for arbitrary flow I can write the Percival's equality in this form. So, now you can see we have replaced that summation by integral, and we have written it that L cube, we have written it as 2 pi whole cube by d cube k. So, that is what we have got here. So, this quantity, the kinetic energy per unit volume, is called the kinetic energy density. This is of course a scalar quantity. I am going to do integral over all possible k's, right. So, it is in 3 dimensional k space. So, what I could do is I could do it in a slightly different way. So, for example, if I have this 3 directions, I could write it in let us say Cartesian frame. I could also write it in a spherical polar system. So, if I do it in a spherical polar system, then what happens? I am going to talk about the radius vector of the okay. So, that I could call it let us say as k bar, and an elementary volume in spherical polar system would be what? Would be a sort of a spherical shell of width, I will call it as dk. So, what happens to the elementary volume in this case? What we are going to do is, see, there we are talking about 3 variables in the x, y and z direction. So, what we are doing here, here also we are doing the same thing, k bar, and then of course, we will talk about this angle theta and this angle phi, right. That is what we do. However, what we are talking about, let us say we perform the integral in theta and phi direction, and then it becomes what? It becomes a one dimensional quantity. So, basically then looking at a spherical shell like this, we have performed all possible variation in theta and phi. That is how we are getting this spherical shell. And what is the volume of that shell? The surface area is 4 pi k bar square, width is dk. So, that is that, right. So, that is what you are seeing, that if you migrate from Cartesian frame to a spherical polar system, then this elementary volume you could write it in kind of in terms of a single quantity. And what is k bar actually? K bar is the modulus of the wave number vector, because you can take k bar and can project in 3 components that will give you along x, y and z direction. So, basically it is another way of looking at the quantities in a spherical polar system. And then the total kinetic energy that we have gotten, what we are going to do is, now we are going to integrate over the remaining unknown independent variable k bar. So, I will integrate that over all possible k bar, I will get the total energy. Okay. So, if I write it like this, and if you have seen that previous expression that I had written for E of k, that involved d cube k, remember? If I substitute it here, so I will get this quantity times 4 pi k square, that should be my E of k bar, because I have to just simply perform that k integral. So, that is what we are going to get. Okay. So, from each length scale I can identify corresponding k bar, I get the corresponding contribution of the energy spectrum. Now, you may like to know what constitutes this E of k bar. See, going back to our original equation, not this, the original equation which also included the body force. The body force can directly stimulate a particular length scale at whatever scale that is happening. Okay. This is what we are going to study now, and we are going to show what the nonlinear terms do. The nonlinear terms actually provide a kind of a coupling among different modes in k space. Okay. In the real space, when I look at the nonlinear term, what do? They are responsible for all kinds of instabilities. That is what we have studied, right. Instabilities of long wavelengths, which also gives rise to, via the dispersion relation, and also nonlinearity will give rise to smaller scales. Okay? Since these nonlinear terms arise out of the inviscid operator, of course, there is an inviscid operator, right, convective acceleration term. So, what happens is this nonlinear energy transfer that takes place between two wave number is going to be conservative, because it is inviscid mechanism, no losses involved. Okay? So, that is what we are saying, that we have to look at the nonlinear contribution. If we want to study, we do not need to really look at the viscous part. We can just simply look at the inviscid operator and see what this nonlinear contribution is going to be. So, we are trying to understand what this nonlinear energy transfer mechanism is. To help us in understanding that, let us define a quantity which we will call as the entropy. Entropy by definition would be nothing but mean squared vorticity integrated over the whole domain. That is what we are defining it as, that omega square integrated over the whole volume, that is our entropy. This of course, is a global measure, because we are integrating over the whole domain. Tells you about what is the total vorticity content in the flow. To understand creation or destruction of entropy, we need to understand the role of vortex stretching mechanism, which we have alluded to before, but let us spend a little time understanding it in somewhat little more detail. Now, if I look at the 3D Navier-Stokes equation and take a curl of it, I will get the corresponding vorticity transport equation. Here every term is involved, even if the body force is non-conservative, this will be non-zero. If it is conservative, this will be 0, right. But you can also see the viscous term, and this is the term that we are talking about as the vortex stretching term. Okay. Omega by definition is nothing but the curl of the velocity field. Now, if we consider the inviscid flow and we also ignore any non-conservative body force, then this equation can be significantly simplified. So, basically what we are talking about, we are talking about a vorticity transport equation for 3-dimensional flow, which is inviscid and which is not affected by any non-conservative body force. So, this is your equivalent vorticity transport equation. This is what we are calling as vortex stretching term, and we have already noted that this is present only for 3D flows, because in 2D flows these two operators are orthogonal, omega and the gradient operator. So, this is identical equal to 0. Okay. So, this particular term that we see on the right hand side of this equation has a role to play for 3-dimensional flow only. Now, think of a cylindrical fluid element whose vorticity, let us say, is aligned in the z direction. So, that is what we are showing, omega is in this direction. Let us say the top of the element has a velocity u t and the bottom part has a velocity u b. So, what it is doing actually then, it is elongating the fluid element, right. So, what is happening is, if I take the velocity as a linear function of z, that means if z increases, v also increases. So, then of course, it is going to be stretched in the z direction. So, this is what we want to see. So, we called it a vortex stretching. So, we are talking about a situation where we are increasing the velocity in the z direction. So, what does this do? So, this is now going to be a positive quantity, right. That is what we are saying. So, as a consequence, the fluid element will be stretched. If the fluid element is stretched, and we are talking about inviscid dynamics, so there are no losses. So, everything has to be conserved, including the angular momentum. And what is angular momentum? I times omega. So, if I angular, well, wrong choice of variable, but its angular momentum is this, that is proportional to moment of inertia times the angular velocity. Okay. Now, what will happen if I take an element and I stretch it in the z direction? What happens? I comes down. If I comes down, what happens? Omega has to increase, because this is anyway conserved. So, what we are saying that if I have a velocity field which causes the fluid element to stretch, that also causes the vorticity in that direction to increase, intensify. So, this is one mechanism by which vorticity increases, right, and it can increase if this term is positive, it can decrease if this term is negative. But irrespective of whether it is increasing or decreasing, if I look at the entropy term, what will happen? It will always increase. See, that is why we purposely introduced that quantity, which is nothing but the mean square term. So, whether the element is stretched or compressed, entropy is going to increase, and that will tell you what is the rotationality of the system, right. Now, we have very clear here that this vortex stretching term that we are looking at does not increase or decrease the total angular velocity because of the conservation, right. We are looking at in one direction it is increasing. What happens to the other direction? Because totally we are again looking at inviscid mechanism. I omega has to remain conserved. So, if the I is all pervading, that is not changing. So, omega also will not change. So, that is exactly what we are saying here, does not increase or decrease the total angular velocity, okay, but it simply acts like a local amplifier or attenuator of the vorticity field. So, let us generalize this result by looking at the nth moment of the vorticity field. So, what I am trying to do is I have omega raised to the power n, integrate it over the whole domain and find out its time rate of change. Okay. So, if I do that, of course, I can bring it inside, then I will get n times omega to the power n minus 1 del omega del t integrated over the volume, and this we have already obtained from the inviscid vorticity transport equation, right. So, this plus this is the convective term, this is that vortex stretching term. So, I can replace this del omega del t by this 2 term, right. So, that is what we are going to do. Now, if I do that, what do I get? Well, I do get this 2 sets of terms, right. Now, this is easy. The second term is easy because this is going to give n times omega to the power n dot grad u. Now, this part I have written it in this form. If you open this, then what will you get? You will get omega to the power n, and then you will get del dot u term, but del dot u is 0. So, that is why this term has been written like in this form. So, again we note that this term is coming from the stretching term. So, this stretching term is missing for 2D flows, and what happens to this? I am going to perform this volume integral. So, I can use the divergence theorem and write it in terms of a surface integral, Gauss divergence theorem, right. So, basically what I have done, I have taken the quantity, found out its normal component, that is on the domain boundary del of omega, and that I do a surface integral. Now, this quantity itself, if I look at the whole volume, what may happen? If I go very far away, the effect of the body will not create a non-zero omega. Again on the body omega will be non-zero, but u will be 0 because of no slip. Well, let us understand that. So, what will happen is this first term will be most of the time equal to 0 because of, and please do understand we are talking here about inviscid dynamics. So, we are not even talking about creating omega at the wall. Even if I talk about creating omega at the wall, I will have to correspondingly talk about no slip condition. But if I talk about inviscid dynamics, then u will be non-zero at the wall, but omega is not getting created. So, basically that is what we say here, the first term is 0 because of boundary condition. Okay. And if we are talking about two dimensional flows, then instead of doing a volume integral, I will be doing a surface integral, and then this term will be a surface integral. I can use a Stokes theorem and convert it into a line integral, right. So, the analogy is very simple, either I use a Gauss divergence theorem or the Stokes theorem. In either case, what I will find that the first term will go to 0, and for the 2D flow, of course, the second term also is additionally 0. So, what basically it says that in 2D flow, any order moment that you look at for the whole flow field does not change with time for 2D flow. For 3D flow, what happens is only thing that comes about from this stretching term, right. So, this nth moment increases due to this vortex stretching term for 3D flows, right. So, to stretch it to extend it to viscous flows, we would have to basically replace del omega del t by not only this two term, but also the viscous diffusion term. This term also will cause omega to the power n to change with time. Okay. So, that will be additional source of change, and moreover for viscous flow, no slip condition at the wall will be the source of major vorticity production. So, this is what we need to understand. Now, look at some additional properties of entropy. This is the way the entropy is defined. Okay. This are all tensorial notation. So, we have this permutation symbol here, epsilon I j k times del u k del x j. So, what does it mean actually? We are looking at omega I, right. So, this is your omega I, that is how it is defined, because you are integrating over j and k. So, what is left is basically the omega I part. The same thing here, what is this? This is going to be omega j. Okay. Well, that is what we are doing, and individually the property of this permutation symbol is the following, that if I take a cyclic permutation, that means if I go in a natural cycle, I take say I equal to 1, j equal to 2, k equal to 3, that is a natural cycle, or I could take I equal to 2, j equal to 3 and k equal to 1, that is also natural. So, it is basically you are going in circle, right, and or I could take it 3, 1, 2, etc. Then the permutation quantity symbol takes a value of plus 1. If I interchange any of these two, so I take, instead of taking 1, 2, 3, I take 1, 3, 2, then that becomes minus 1. And if two indices are identical, then this quantity is 0. That is the meaning of the permutation symbol. So, if you adopt this way of looking at entropy, you can also write down the entropy in terms of this. Once again, you can notice that these are two products of delta function, Kronecker delta, and you can very clearly see that this multiplied by this, they will be non-zero when j equal to m and k equal to n. That is what I have done here, right. So, here I have changed n to k and here j equal to well, I suppose, yeah, this has del x m has become del x j. So, that is that path, and this path will give you this. Now, this is nothing but this quantity, right, is not it? See, recall that quite often than not we were writing the contribution coming from this as nu times modulus of grad u square. So, that is because of this term. What about this term? This term is going to be 0 if I am looking at 0 or period for this is going to be 0 if I am looking at a periodic problem or if I am looking at the boundary contributions coming out. No slip boundary will ensure that. Okay. So, basically then what we are essentially talking about is the entropy is also related to the gradient of the velocity field by this. Okay. So, we can use this expression in energy equation for the total velocity field. Again we start from, let us say, this equation that we have already written for the Navier-Stokes equation, including the body force term. Now, what happens is that equation that we have written in the previous step, I will take a dot product of this equation 6a with a velocity field. So, basically I will multiply it by ui and integrate over the whole domain, and this will give us this equation. So, I think what I would do here, I will just stop here today, and in the next class we will just wrap this thing up and we will see that how properties of entropy can help us in understanding what kind of additional length scales are involved in this problem. Okay, I will stop here.